Welcome to this tutorial of how to use the ORD interactive editor. We're going to walk through defining a data set based on the paper you see on the left side of the screen, this Jack's paper from Abby Doyle and coworkers. So specifically, we're going to be thinking about entering the data that is behind this figure one. Okay, so we've got a sort of multidimensional screen. We've got a lot of different reactions that were used. We've got different bases, different fluorinating agents. Obviously, those correspond to different yields. What we're going to do is we're going to define the data set in the ORD that captures this information. The general strategy for doing this is going to involve taking one reaction, so defining one reaction through the interactive editor, converting the sort of data that defines that reaction into a template, and using that template in combination with a spreadsheet we've prepared to define the full sets of reactions here. Okay, so we've got a spreadsheet already defining these different conditions that you'll see later. But for now, we've got to get started defining the template reaction. Okay, and what better place to start than with reactant 1A. So we're going to focus on using alcohol 1A, the sort of upper left condition, right? Using DBU as our base and 3Cl as the shorthand for this sulfonyl fluoride. So the first thing that we're going to do is we're going to go to the interactive editor webpage. So this is also hosted at editor.openreactiondatabase.org. This is just a local version that I'm running. So it might look a little bit different for you depending on when and how you're accessing it. You might see sort of a login with a GitHub badge up at the top. That is sort of a mode that we would recommend you use. So all of your data sets will be associated with and saved to your GitHub account for authentication. All right, so here I've got sort of an empty session, so we don't have any current data sets available. So what we can do is we can create a data set. We can upload a data set if we've got the PBText file on our computer already, or we can enumerate the data set, which is what we'll use towards the end here. But for now, right, we have to create a data set to store our template reaction. Okay, so I'm just going to call this Gilson, the first author of this paper. We'll create our empty data set, okay, and then it appears in our list. When we open up the data set, what you see is some metadata we can define about this data set. So each data set is a collection of reactions. This one is currently empty. There are no reactions. We'll go ahead and give it a name. So we'll call this the deoxyfluorination, oops, if I can spell, fluorination data set. We don't need to define the ID. That's something that will happen automatically during the submission process. As for the description, go ahead and say that this is going to be data from figure one of this paper we're looking at. So we'll be able to define the paper also for each reaction, but we'll define it at this data set level as well. Okay, we'll go ahead and hit save. So now it's time to start adding reactions to this. And again, because we're going to use the enumerate function, we're actually only going to define a single reaction. So we'll add this in, so reaction index 0, we'll click on it, and then we're in, and we can see now the page for defining a full reaction through the ORD. Right, so there's, this is a fairly lengthy form, right? There's a lot of data one could associate with a chemical reaction, right? Defining all of the species that were used, all of the conditions, and all of the outcomes. We'll go through this example reaction, and we'll see some fields are going to be used here. Many fields will not be used. All of the fields, or most of the fields, I should say, are optional for the ORD, but we, of course, encourage you to provide as much detail as is available from the original experimental record. So just some basic navigation principles here. We've got our header up at the top with some buttons to download the current reaction, to clone it or copy it in this data set, or delete it if we don't need it anymore. There's also a validate button where we can run a validation script over all of the fields defined here. And if we do that, we see that we have 3 errors. So our validation scripts are telling us that this is not, as it stands, a valid reaction entry because we don't have an input, we don't have an outcome, and we also don't have provenance, right? We haven't recorded who I am entering this data. You also see there's sort of an autosave feature, so we don't have to worry about clicking save all the time. You can click this to disable autosave, but we'll keep it on for the purposes of this video. Okay, so other navigation things, we've got this sidebar, which defines the major headers, right? If you click on the sort of different tabs here, you'll just get taken to that point, right? Scrolling through this very long form. We'll just start at the top and work our way down. So the first thing that we can do for this reaction that we're defining, again, this is going to be the upper left corner here, is give the reaction an identifier, and we could give it a reaction smiles, but that's going to be implied by the components. So instead, I'm just going to give it a name, right? I'll just say that this is, again, a deoxyfluorination reaction. So I'll just call it deoxyfluorination there. That's good. Now we move on to defining the inputs of the reaction. So the inputs are going to be every chemical that goes in the pot, right, aside from workup steps. So for this reaction, it'll include the alcohol, it'll include the sulfonyl fluoride and the base. And actually, it's going to be a little bit different how we define the inputs than what's shown on the manuscript. So in the ORD, we're trying to capture what actually happened physically in the process, and what was added was not pure species. You have this alcohol, sulfonyl fluoride, base, and then THF to balance. What was added were stock solutions. Okay, and we can see that if we go to the supporting information for this paper. And so here, of course, we're working with a published paper already, so we're going to be digging through the SI to find out the details. If this is a reaction that you've performed, you, of course, will have the details in a different format. So the data behind figure 1 is sort of described in this second section here, the high throughput experimentation. And so what we're going to do is sort of parse the information here by hand and record what happened in the format of the ORD. Right, so we're dealing with inputs first. So you'll see there's already one input that's sort of pre-populated on this form. If we look to the SI and we figure out, okay, what actually happens, the reaction sort of started by charging a vessel with a stock solution of the alcohol in THF. Okay, and we know the alcohol varies, so I'm going to go ahead and just say this input, which is going to be a stock solution, is just the alcohol in THF. So this is one solution, so it's one input, but it's going to have two components. You can already see that we have a validation error here because we have an empty input, right? So inputs require at least one component. So add the first component, right, by clicking that add component button. That's going to bring down this component sort of set of fields. So first I'm going to define the reactant species, right, because we have the alcohol in THF. So the reactant is going to be this alcohol 1A. This is the limiting reactant, right, relative to the sulfonyl fluoride, it's limiting. To define the chemical species, we can use a few different techniques. So we can directly add an identifier. So we can define sort of a name, a smile string, cast number, a lot of options there. What I'm going to do here instead is draw the structure. So we've got a catcher integration here. So it's pretty convenient to just draw the chemical structure of these molecules. So drawing doesn't have to be too pretty. It'll get cleaned up automatically when we hit done drawing. And so here we can see that we've got a mol block populated from catcher, and then we also have the smile string sort of as drawn. So we'll go ahead and leave this in there. Again, we're automatically saving, so we don't have to worry about doing that. We can see that we've defined sort of the component 1A from the form. Now we move on to defining the amount of this component that's present in the inputs. So if we see that we are running this reaction at the 0.4 molar scale, and we see that the stock solution has 0.1 millimole of the substrate and 125 microliters THF, we'll define the amount of our alcohol then in terms of millimoles. So we define moles, 0.1, we select millimoles for the units, right? It's important to capture these units in a structured manner. We can then add any preparations, which we won't for this alcohol, but we'll see for the THF in a moment. We can also add in information about where this compound came from, right? So vendor information. Right, so that's it for the alcohol. We then need to define the second component of this input, which is going to be the 125 microliters of THF. So for that, we can just look this up by name. That's easy enough. So compound name THF, and that's already going to get populated here. So we see, yes, that is in fact THF. Its amount is going to be defined by volume. So the value is going to be 125, and we'll select microliter from the dropdown. We can also specify that the volume here includes solutes. So, if you imagine making a stock solution where you fill a volumetric flask with your solid reagent and you fill up to the line, that's of course a volume that includes the solutes, right? And this isn't as much an issue for these fairly dilute solutions, but if you have very concentrated solutions, you can imagine knowing whether this is volume of pure solvent or the total volume of the solution can actually make a difference. So in this case, we're going to say that this volume does include solutes, right? Sort of making a small inference based on how the stock solution was likely prepared. Now, for this THF component, we're going to now investigate the preparations. So there are a few different ways we could think about preparing these components, right? You can think about purifying species after you order them. You can sparge them, dry them. You can even have them be synthesized, right, if they're not purchased. And in this case, from the SI, again, we see, if we read this closely, right, that the THF, toluene, and other solvents were dispensed from a dry solvent system. So that means we'll go ahead and define that here, right? So preparation, dried. There is some information in the SI here about the vendor sources. For this tutorial, we're not going to bother entering those, however. Another field that I didn't emphasize for the alcohol component is we can add features. So if we have maybe a special catalyst species that we're adding, we can add features and descriptors or arbitrary data files corresponding to them. So this is good if you want to add sort of expert descriptors to the components, but in this case, there's no need to annotate them. So we're still in this input selection, and so now we get down to the addition information. So this is going to be defining the order of addition starting at an integer of 1, right? In what order were these different stock solutions or species added? We know from the SI here that this was the first solution added. So addition order is going to be 1. If we knew the addition speed explicitly, we might specify that it was fast or slow, could be dropwise. The addition device, again, we could specify if that were defined. It's not, so we're not going to make any assumptions. There's also addition time, right? So maybe we let the solution sit for a while before we add it. There's the duration, so how long, right? Over how long of a period did we add it? So that's important if you have dropwise addition. And then addition temperature. So maybe we cooled this down to 0 Celsius before adding, right? In this case, we didn't. So all we have from the addition information is the order of 1. Now, flow reactions are compatible with the ORD, and so we would in that case need to define a flow rate, the rate of addition of the stock solution. But of course, we aren't doing that here. This is a simple, I shouldn't say simple, this is a batch screen. Right, so that gives us our first input, which is going to be this alcohol in THF solution. So we have another 2 inputs to add, so we'll go ahead and add one here. This is going to be the second component, which is the sulfonyl fluoride, also in 125 microliters of THF. So we'll go ahead and call this sulfonyl fluoride in THF. As you'd expect, this is going to have 2 components, right? One is going to be a reactant. Let's call it a reactant because it does contribute a heavy atom. It contributes a fluorine. It's not the limiting reactant though. To define the compounds, right? We're doing this upper left corner for now. So this is going to be 3Cl, so this sulfonyl fluoride. So we'll go ahead and draw it again. That seems like the easiest way to define it. So we stick that aromatic ring in here. And go ahead and draw this compound. Again, as you might be used to these drawing tools, you don't have to worry about whether they are pretty as you're drawing them. Just have to have it defined. Let's see, that doesn't look like it was defined properly. No, that was not. Let's go ahead and pull this up again. I think my double bonds might have gotten messed up there. Let's go ahead, fix that up. Great. Now that looks right. So we've got this again from Catcher. We have the mole block as we drew it, and we also have the smile string there. Okay, for the amount, we know this is 1.1 equivalents, and so the stock solution has 0.11 millimoles, so we go ahead and define that. 0.11 millimoles. Again, we skip over preparations and source. Okay, so now we've got solvents here. So here we've got, again, THF. Still have 125 microliters. So go ahead and define that. It's still dry. So go ahead and define that. Actually, let me just go back up to my alcohol and THF. And let's see. Yes, I forgot to specify the solvent role for that stock solution, so we'll fix that. Great. So I've got the two components defined for this input. We still need to define the addition order. So this is going to be a sequential addition. So we'll call this addition order 2. And again, no details about speed or temperature, so we leave them as is. Now we've got our third input, so this is going to be the base in THF. So this is going to be 1.5 equivalents, still in 125 microliters. So the template reaction that we're doing is DBU. Go ahead, don't have to draw DBU, so we'll look it up by name. It gets parsed correctly, we confirm by the structure. Because we have 1.5 equivalents, we know that's going to be 0.15 millimole. And as before, let's go ahead and add in 125 microliters of dried THF. Excellent. All right, so that should conclude the 3 inputs that go into this reaction. So let's go ahead and hit validate at the top bar to validate the whole reaction. You can see that the number of errors in the system did go down by 1, right? So we've defined inputs, but we still don't have any outcomes or the provenance of this reaction, but we'll get to that soon enough. I'm actually going to scroll us back up to the summary at the top, where we can see that we're starting to see this visual depiction of the data as it's been entered. Okay, so this graphical depiction is not going to contain all of the details and all the information about what we put in, but it's going to contain sort of a high-level summary. But actually here, checking the summary, I've noticed I forgot to put the addition order for my base in THF, right? That's the 3rd addition, so I need to fix that. So we go down to that input, we'll enter that addition order, hit save, validate, take us up to the summary. Now we see the correct ordering. It's great. Okay, but we still have nothing on the right side of the arrow, right? We don't know anything about how the reaction was run aside from these components that were put in. So we're going to go down to the next sort of major header, which is going to be the setup of the reaction. So the setup is just defining the details about the vessel, right? In what vessel was this reaction performed? Let's go back to RSI. Okay, so we see that we use an 8 by 40 millimeter glass vial, the 5 millimeter Teflon stir bar. So we'll get to the stir bar later. Here, though, it's important just to note that this is a glass vial. The volume is about 1 mil of that. So we'll say the vessel type, right, of these many different options is going to be vial. Material is going to be glass. And we'll say that the volume is about 1 mil. Right, for the vessel size, the precise volume of these sort of small vials defined in terms of lengths should just be converted to volumes. Okay, so we also can define if this was an automated reaction. So was this set up by a liquid handler, for example? In this case, it was not. So we can leave this as false or unspecified if we like. We can also specify the environment of how the reaction was performed. So was it then in a fume hood, just open on the bench top, or in a glove box, or in a glove bag? And here it's not explicitly stated. I think one could argue it's probably being done in a fume hood, but we don't know. So we're going to leave that as unspecified because I was not the one that ran this reaction. We can also add details about the vessel preparation. So maybe we had an oven dried flask, right? Or maybe we purged the system before we started adding material to it. In this case, we don't need to worry about that. It's not specified. We also have vessel attachments, where we can say what was added, if anything, to this glass vial. So maybe we've got a thermocouple in there. Maybe there is a balloon on top. Maybe it's hooked up directly to a gas adapter. In this case, we have a capped vial. Okay, this is going to be, if we read a little bit later in the SI, we know that the vials were capped and stirred for the reaction. So we specify that there was a cap on our glass vial. That takes us into starting to define the conditions now. So we get to the conditions, and first one we define is the temperature of the reaction. Okay, so if we refer to the SI again, the reaction took place at room temperature for 48 hours. Okay, so the control for the temperature is not active, right? There is no oil bath, water bath, sand bath, any of these other options, just ambient conditions. If we sort of try to validate the temperature, we'll get a warning. This warning is going to tell us that even if we're using ambient temperature, we should specify room temperature, right? Everyone has different definitions of room temperature. But because, again, we didn't run this reaction, we don't actually know. We're not going to guess if it was 20, 25. We're just going to leave it blank. And that's why this is a warning, not an error. Okay, so temperature control, it's ambient. That's all we know about it. We move on to pressure control. Right? There was no explicit pressure control, but we do know this was a sealed vial, right? So it specified that it's sealed. We don't have a pressure set point like we might if we had a constant positive pressure. And for the atmosphere of this reaction, we know that these were just run in air. So it's just, again, ambient conditions. And so an air atmosphere is what the solution saw. Move on to the stirring. So again, if we look at the SI, we know that we have a 5mm Teflon stir bar stirring at 600 RPM. So the stirring type, we don't have an overhead mixer, we don't have sonication, we have plain old stir bar. If we like, we can fill in these details, right? So we can say that this was a 5mm Teflon stir bar. As for the rate, we can enter a qualitative rate, right? Just low, medium, high, or we can enter a numeric rate, right? 600 RPM, because that's actually known. Now, other aspects of the conditions include if there was illumination, right? If we were running a photochemical reaction, we'd want to specify what type of illumination we had, the wavelength of it, if it was a single wavelength, the distance from the vessel, the color qualitatively of the light. We don't do that here. If there were an electrochemistry reaction, right, we would want to specify the mode of running our electrochemical cell and any details about anode cathode materials, right, constant current or voltage, etc. Again, don't worry about that here for this batch reaction. And then for flow, we would want to specify what type of sort of flow vessel was used, what type of pump was used, what type of tubing and its diameter was used. But again, this is a batch reaction, and so we skipped these fields. Now, the final few sort of fields for the reaction conditions let us specify if there was reflux used, if, for example, it was adjusted to a specific pH, or if there are other details we want to specify, especially if there are what's labeled here as dynamic conditions. Okay, so dynamic conditions is essentially just saying whether there are aspects of the reaction conditions that are not reflected in how we just defined them. So this could be the case if you have a reaction that stages different temperatures. If you've got temperature ramp, let's say that your reaction started in an ice bath, but you let it run for a few days, and by the end of it, the ice had melted and the bath had warmed up to room temperature. That, of course, would not be able to be captured in this single sort of ice bath field, right? You'd want to note somewhere that you did let it warm up over the course of the reaction. And so that would mean you'd select true for dynamic conditions and you provide those details in this text field here. Yeah, but in our case, we don't have dynamic conditions, so we can select false or just leave it unspecified here because we are describing the reaction adequately with the above fields. So that takes us now into the next section. So any notes about the reaction. So this is more for informational purposes than anything else. So wanting to record information about if this is a heterogeneous reaction, right? If there's solids that crash out, that could be useful to know down the road if someone were trying to adapt this to flow chemistry. If the reaction is highly exothermic or off gases significantly, that's of course good to know from a safety perspective. Moisture and oxygen sensitivity and light sensitivity are important from reproducibility and safety perspective. And we allow sort of additional unstructured notes about safety for this reaction, as well as details about the procedure. So we could potentially take some of the information about the procedure from the SI to put it into these additional details, but we'll capture, I'd say, almost all the information that's in this SI document adequately, just given the structured fields. So let's leave this blank for this example. So if we, let's validate actually and go back up to the top. So now we see that our arrow has some of the conditions specified above it, right? So specifying this ambient temperature, air, and high rate of stirring. You also see that the warning we got for the ambient temperature sort of propagated back up to this warning message. So the errors and warnings you see at the top is essentially just the total of the errors and warnings of all of these sections contained within the form. Right, let's go down now to observations. So observations would be, if you note color change, if take a picture of the reaction or the setup, that'd be appropriate to put in this observation section. So you can upload a file, you can define sort of a float value. Maybe you sort of recorded something about the reaction. That's a number. Maybe it's a URL. You want to link to some sort of video that you've uploaded about it. We don't have any recorded observations here, so let's go ahead and remove that. The next section is defining workups, right? So we haven't actually gotten to the outcomes of the reaction yet, but we do have a section to define workup. So anything that happens between what you might call the main single step reaction and analysis. So in our case, if we look at the procedure, we see that sort of after these 48 hours, yields were assessed by fluorine NMR, following the addition of our internal standard in 250 microliters of deuterated chloroform. Okay, so what we're going to do is then define a workup step of this addition, right? So before the analysis, we added this other input. Okay, so because this happens after the reaction, it's defined in the workup section, not as another input at the top. So we'll say this is a workup of type addition. We'll need to define this input. So this input is going to have two components. So again, it'll have our standard 1-fluoronaphthalene, as well as the deuterated chloroform. So here, the reaction role is going to be internal standards. We'll go ahead and look this up by name. So this is just 1-fluoronaphthalene. Okay, and that got parsed correctly, very good. For the amounts, right, in the SI, it's specified as 1 equivalent, which we know to be 0.1 millimole. So go ahead and add that. Let's go ahead and add in our solvent here. Actually, let's call this a workup because it's part of the workup step, even though it's a solvent for this 1-fluoronaphthalene. So we can look this up by name as well. So the name resolver uses sort of an NIH resolver as well as the PubChem resolver. So it actually has a decent number of chemicals in it. You should always, of course, check that the structure that gets parsed out looks good to you. In this case, yes, this does look like deuterated chloroform, so that's good. As for the volume, we know it's 250 microliters here, and it's not obvious if this is meant to include the solutes or not. Maybe there's a 250 microliter ampule that they use, so we'll leave that as unspecified. Okay. As with an input, because this is a workup addition, we could specify, if it were cooled, if it were added slowly, but we don't have that information here. So presumably it was added all at once, but we don't know that for sure. Okay, so this is our workup addition then, that's defined as these two components as part of that stock solution. All right, so we've finally gotten down to the outcomes section. So the outcome of reaction is defining any sort of analysis, any characterization, any quantification, and identification of products. So most single-step reactions, right, unless you're doing a time series analysis, are going to have one outcome. So here that is the case as well. We've got one outcome and it occurs at 48 hours, okay, because that's the reaction time here. We don't factor in, the small amount of time it would take to do this workup step in Quench. The reaction time is 48 hours. We can specify the conversion with respect to the limiting reactants. In this case, that's not actually computed or measured, so we don't do that. And then we can add in the analyses in product species that were performed or identified or analyzed at this 48-hour mark. Okay, so we already know that there's fluorine NMR was used to characterize the yields. So let's go ahead and add an analysis. The name of the analysis isn't used for anything other than internal bookkeeping. So we'll just call this 19F NMR. The type of analysis, you can see we've got a few sort of common analyses defined here, is going to be NMR other. And as details, we'll just go ahead and put in fluorine NMR just to be explicit about it. We can define sort of the idea of this analysis according to the CHMO ontology. Let's not bother with that for this tutorial. If we'd like, we can define the instrument manufacturer, calibration dates. Here, I think the instrument manufacturer is specified in the SI if we look at the instrumentation section. So let's see, fluorine NMR spectra were recorded on one of two instruments. So we don't actually know which one exactly it was, but we do know that it was a Bruker. So we'll go ahead and put that. If we knew exactly which one it was, we would put the frequency in the details fields, but we'll just put 19F NMR for now. We can also specify for this analysis if it was intended to be of an isolated species, right? So in this case, it's explicitly an analysis of the crude reaction mixture, so it is not of an isolated species. But you can imagine if we did some isolation and workup, maybe we did some sort of UV, melting point, IR characterization, that would have been of the pure species, right? The typical sort of product characterization you could do, right? And sort of proton and carbon NMR. But this is a fluorine NMR of the crude, so this is false. We can add data for this analysis, so we could upload the spectrum, right? If we had the file, so we could upload that file here. We don't have that, we don't even have the peaks here, so we'll go ahead and leave that blank. We won't add any data. This was the only analysis performed for these reactions, so we don't have to add a second or more analyses, we just add a product here. Okay, so for the products, we want to define the outcomes that were characterized, right? The species that were formed. So the reaction role in this case is going to be a product. This is the desired product that was characterized. So this is going to be 2A, right? This is going to be the fluorinated version of this species 1A. You might think it's a little bit silly to have this reaction role drop down here, but actually, if we want to quantify the amount of leftover starting materials of some of the reactants or reagents, or if we want to define explicitly peak areas in an LC for internal standards, we would define those as quote unquote products, but with their corresponding reaction role, right? So if it were leftover reactant we were characterizing, we would assign the reactant role as reactant. Okay, but here we just have one species characterized. That's our desired product. So let's go ahead and draw it. That's probably going to be the easiest way to do this again. We could of course copy the smile string and just modify it. That's a little bit more work. So we'll go ahead and draw the species. Again, doesn't have to look pretty. Done drawing. Great. So we see we've got the mol block again, we've got the smile string. It's drawn correctly. The next very important field is a list of measurements. Okay, so these measurements can contain measurements with respect to the identity if we're using an analysis to confirm the identity of a product, or the yield or the selectivity. It could be an uncalibrated peak area, right? Or if it's just percent by UV area in an LC trace, maybe we would call it a purity, right? UV purity. If we are using mass spec for quantification, again, uncalibrated, maybe we just call that an intensity at a specific EIC or an integrated EIC. But for this use case, we're dealing with yields, right? We're dealing with quantitative yields, right? With some error, of course. So these product measurements need to be linked to a specific analysis that was used to get that measurement, right? So here we're going to be quantifying the yields based on our 19F NMR analysis, right? You can see that's the only analysis we have to choose from. If we had done a lot of different characterizations of this, maybe we would have one method used for identity, another method used for yield. And so it's important to know which analysis was used for which type of characterization. The value of the yields, if we go back to our figure 1, again, this upper left corner is the template we're still working with. That's going to be 40% yield. Now, we don't know the exact uncertainty for this specific experiment, but if we look at the SI, there was some attempts done to characterize typical replicate errors, right? So the average variance was about 4.8% according to this SI. So let's go ahead and say that this is 40 plus or minus 4.8, right? It's of course an uncertainty. It's not precise, but it gives us some ballpark precision, right? Now, we also want to specify that this is a true yield in that we used an internal standard. It is also normalized to that, right? Presumably that was used in the calculation of this yield. And if we were doing sort of LC, peak areas to get the yield, we'd want to know, was there an authentic standard used to develop a calibration curve? In this case, there's no evidence that an authentic standard was used, and the exact shift of the fluorine NMR was used to sort of confirm the amount. You don't need to do that for fluorine NMR here anyway. So we'll leave authentic standard as unspecified. Okay, and that's, we're still in the outcome field, right? So we've defined the analysis, the fluorine NMR. We defined the product, and within the product, we've specified a product measurements as well. Okay, there's also some details we can specify. If we were isolating the product, we could qualitatively describe its color, right? Its texture, if it was a nice powder or a wax or an oil. We could also define features of the product, just like we could define features of components as part of the input. Right, so now if we hit validate, let's go back up to the top, we see that we now have our outcomes specified to the right of the arrow. We get the summary that this product was observed in 40% plus or minus 4.8% yield. Now, the number of errors in this reaction has decreased down to 1, so we're just missing the provenance, but the scripts recognize that we've defined the inputs and outcomes appropriately. Let's go down to the provenance and finish things up. Okay, so in this provenance section, we can define details about the experimenter, right? So who actually did this reaction, or where was it originally reported? In this case, we can sort of infer right from the publication and where these experiments were performed that these were performed in Princeton. We don't know when, the time that the experiment was started, so we don't bother with that. The DOI, we can of course pull from the paper that we're referencing. That's how we're getting the data. If you're doing unpublished data, you of course don't need to specify the DOI, that's fine. And then the publication URL, we'll go ahead and put in here, just the PDF URL. Okay, and if you wanted to, I guess we could also say this was Princeton University. But importantly, I'm not going to assume who the experimenter was among the authors of this paper, right? We'll just leave that blank. Now, the record creation is another part of the provenance. So this isn't, who did the reaction, this is who's now entering the data. And so what we're gonna do is we're going to say that we're creating this record now. So it'll put in the current timestamp. It wants to have some accountability, right? In case there were some serious errors here, in case there are questions people have. So we're going to go ahead and put in my information just for completeness. Let's go ahead and copy in OKD, great. And we'll go ahead and hit validate for one last time now that we've added the provenance. And we see that at the reaction level, we have no errors in this record. We've got our one warning about room temperature not being defined, but that's appropriate, right? That's an acceptable warning to leave. And now we have the full reaction defined, right? This is the full templated reaction corresponding to this square of figure 1, right? This 40% yield under these specific conditions. Okay, so now this is where we want to take this template. We want to generalize it. We want to allow the alcohol species to vary, the sulfonyl fluoride to vary, the base to vary. And we want to use it to define an enumeration, right, of all of these different conditions that we have defined in a spreadsheet. So let's go ahead and to do that, we're going to download this reaction. Okay, so let's go ahead and download here. You can see all my download folder. We'll go ahead and download this reaction.pb text. I'm going to go ahead and open that up in a text editor. I'm just going to use Sublime in this case. So if we sort of look at our text window here, we've got a text format of all the information we've just entered. Okay, so we've got our identifier listed at the top, a deoxyfluorination just as the name of this reaction, this generic reaction type. We've got our inputs defined, sorry, 3 different inputs. We've got our setup, we've got our conditions. We've got workups, outcomes, right? All this information is present, including the provenance there at the end. Okay, so this is what the data looks like on the back end, right, of what we've just defined on the form. But to do the enumeration here, we're going to want to allow the species, right, the reactants, the product to vary as well as the yield. And actually, I already have a prepared spreadsheet I'll pull up here, which is defining what changes, right? So it's defining all of the variations that appear in figure 1. So I've got a spreadsheet, so each row is just going to be one reaction. Each column is going to define a different aspect of the conditions that varied. So here, the only things that change are going to be the identity, which I've recorded here in terms of the SMILE string, the alcohol, sulfonyl fluoride, base, corresponding product, and then of course the yield. Okay, so everything else, the fact that it was 1 ml glass vials, sealed with a cap, stirred at room temperature for 48 hours at 600 RPM, that's all the same, right? So I don't need to go through the effort of defining that for every single one of these 80 reactions. Now, to do this enumeration, though, what we're going to do is edit. We're going to make some manual modifications to this reaction PB text file. Okay, so what we're going to do specifically is we're going to replace certain fields, right? So instead of having this specific smile string for alcohol 1A for that one reaction, we want to be able to define any of these sort of alcohol smiles, right? We want the enumeration scripts to pull from this list. So what we're going to do is we're going to delete this mole block identifier, right? Because this is sort of redundant information for the purpose of this enumeration. We're going to delete drawn with catcher because these smile strings are not going to be drawn with catcher any longer, right? They're pulled from the spreadsheet file. And we're going to define these sort of placeholder values, so alcohol smiles. I'm going to put that, surround it in $signs, so the script is going to know that this is a template. And when it looks at this PB text file and it tries to parse it, it's going to look at my spreadsheet and it's going to try to pick out, right, which column has the title of alcohol smiles. I'm just going to use that and substitute the value into this position, right? Importantly, we're going to keep the quotation marks because it still needs to be a string. Right, so THF as a component doesn't change. We're going to leave that. That's fine. DBU, right? We also want to let the base vary. So in this case, we're going to get rid of the name identifier because they don't all have the same names. The smiles here, right? It's no longer true that the name is resolved by the PubChem API. Instead, it's going to be pulled from the spreadsheet. So again, we define our base smiles placeholder. We get to the sulfonyl fluorides. And again, we don't want this mole block because we don't have a column defining the mole blocks. So instead, we're going to define this placeholder here, sulfonyl fluoride smiles. And then we're going to delete this detail of drawn with catcher because again, we're pulling it from the spreadsheet. It's not drawn with catcher. All right. So we still need to define the product smiles and the product yield. And again, everything else in this template is going to stay the same. It doesn't vary between these 80 reactions. Workup, right, that's the same. Outcome time, it's still 48 hours. Here we get to the product. Again, we don't want the product mole block because we don't have that in our spreadsheets. The value for the product identifier with type smiles is going to be product smiles. Go ahead and replace that. No longer grown with catcher. Now we get to the yield, which we have to template as well. So instead of saying it's 40.0, we're going to say it's product yield because that's what we've named the column in our spreadsheet. Okay, so once we've done that, we're going to keep the precision as the same. We're not going to use quotation marks because this is a float value, right? It's a numeric value. It's not a string that we're defining. So we don't need those quotation marks. We save this template and that's all we need for the template, right? So this is going to, this defines sort of the pattern, right? Between this PB text file and our spreadsheet, that defines all 80 of these reactions. And so now it's just a matter of generating that full data set. So to do that, we're going to go back to the website. So let's go ahead and pull these two here. I'm going to click back on this Nielsen to go back to the data sets. I'm going to go up one more step to get to the sort of home page, and I'm going to click enumerate. Right, and so it gives you some help in case you're doing this from scratch, not just following this tutorial. So the template file name, let's go ahead and put in that text file we were just editing. For the spreadsheet, let's go ahead and put in the CSV. Okay. Now we're going to hit the enumerate button, and it shouldn't take too long because this is a fairly small data set, right? Only 80 reactions. And now you see that we've got a data set, Nielsen Fig1 data sets. And just point out briefly that that name is based off of what our CSV was called. Okay. So we click here. into the Nielsen Fig1 dataset. There's no automatic population of sort of the dataset's name and description. So actually what we should do is probably put that back in. So we'll say deoxychlorination from Nielsen paper. And for the description, let's just say data from figure 1 of here. Let's hit save. Great. The important part is that we see that we have now a long list of reactions. We have 80 reactions, right? 0 indexed, corresponding to these 80 rows in our spreadsheet, right? So each one became a new reaction according to the template. So let's go ahead and inspect one. So the first one, I believe, should be this upper left corner based on the order that they're defined. So if we pull that up, we can visualize it. We see, yes, indeed, this is the upper left corner. It's the first row in the spreadsheet. We've got the addition orders right. We've got the right components. We've got the right outcome. Everything looks good, right? And the whole form is defined sort of according to the template, but with these substitutions that we've made. Let's go ahead and look at the last one, right? So the final reaction in this data set. Go ahead and open it. It's taking a second to load. And here we see that it's sort of another fully defined reaction, right? All the fields are filled out in the form. We see the summary in the top, a little bit wider, let's make that bigger. And we can see that this last reaction is one that involves alcohol 1D. Okay, that's defined correctly, right? It's convince yourself you just have to rotate this. It's the same into the right stereoisomer. It's just displayed in a different manner. We still have the right sulfonyl fluoride, right? If you look at this PBSF, we've got the right base, BTPP, and then the product, this outcome is 48 hours still, corresponds to the sort of analog of 1D. So this is the correct product 2D, and the yield that's recorded is 58% plus or minus 4.8. Again, because 58% is exactly what we specified in the template, right? Pulling from this figure 1 table. Okay, and that's the way you enumerate a data set with the ORD. So we went through the efforts. If we go back to our home page, right? We went through the effort of defining a template reaction in some detail, right? It required looking at the paper, it required looking at the SI. If you're defining this for a data set that you generated, you might know all of these details sort of off the top of your head, and it'd be much faster. But once we defined that template reaction, we pulled up our text editor. We did a little bit of manual modification to replace values with these placeholders. Those correspondence to column names in our spreadsheets. Then we ran the enumeration. We got this new data set, which contains, right, all 80 of the reactions as we desired. And you can click on this download button to download this data set PB text file. And that's what we would use then when submitting this data set to the official ORD data repository. But this video has at least taken you through the steps of defining a full reaction, using that reaction to generate a template, which in combination with a spreadsheet can be enumerated into a complete data set. And this is really the workflow that makes the most sense for high throughput screening, where we have maybe not just 80 reactions, but hundreds or thousands of different reaction conditions. So thanks for listening or watching this video. Hopefully this gives you a good sense of what it's like to define data with the ORD. If you're volunteering in the beta testing phase, we'd of course welcome any feedback. Really excited to get more contributions to the database. And feel free to reach out if you have any questions or concerns. So thanks very much.